Okay, thank you for the organizing committee for inviting me to this very nice online workshop. So my name is Yijun Yu. I was previously a postdoc from Stanford University Harry Huang's group, and now I started my own group late last year in Fudan University, Shanghai. And so today my talk is based on the work in Stanford, and the title is Superconducting Bilayer Nuclear Thin Films and the Compressive Strain. Let's see. It's not moving. Okay. Yeah, I would like to first acknowledge my all the collaborators, including the group leader, Professor Harold Huang, and Dr. Enkiko, who started this project. And today, the most data I talk about was done by the experiments were done by Yi Liu and Yao Tang, and also we had a very good collaboration with Barrett and David Group, and Lopa in Cornell. And also, we have our BingMine X-ray spectroscopy, mainly done by the Dr. Jerry Lee, and high-field transport by Yute Xu from National Tsinghua University, and ARPA's collaboration from CSM Group, Dr. Baiyang Wang, and our local theorist 3 and colleagues. So today I would like to talk about the thin films and the superconducting barrier thin films in the two of the substrates and some discussions. So I think the press speaker, Professor Meng Wang, has already gave a very good introduction on the bulk barrier nickelates. Actually, this was a little bit unexpected discovery in 2023 that this D75 7.5 electron configuration of this the electrons that can host the superconductivity under high pressure. And in this in the first several studies that they have already raised several interesting questions. So what is the key to the superconductivity? One point that I already mentioned by Professor Mowan that it's this nickel oxygen nickel bond straightening might be the one of the key. And the other possible reason is that under high pressure there is a new gamma pocket appear that might also be very relevant to the superconductivity. So for our thin film community, so we are asking one question, whether the strain can mimic pressure. So here I show this schematics of lattice bounds of the sample under high pressure and extend and the strain. So we can see that in high pressure that all the dimensions of the crystal, the A, B, C, were all compressed. But for the compressive or center strain, it's a little bit different. For example, for the compressive strain, A and B can be compressed, but the C will be elongated because of the Poisson effect. And similarly, for the tensor strand sample, that A and B will be elongated, but the C will be compressed. So DFT actually showed that from left to right is more compressive to the more tensile, and on the rightmost is the band structure that under high pressure. We can see that for this Fermi surface, if we look at Fermi surface, that this more tensile strain, the thin films is more seems more likely to this high pressure study, high pressure band structure, while this more compressive strand samples that have only two Fermi surface, alpha and beta. So then it raises a very interesting question. So whether we should go to this compressive strain region or the tensile region. And actually, initially we tried this more tensile region. For example, we grown these samples on LSAT with around 1% tensile strain, but we didn't see superconductivity. And then switched to this more compressively strain substrate, for example, this lanthanum aluminate with minus 1.2% and still not superconductivity. And finally, when we go to this more compressive strain substrate like strontium lanthanum aluminate, and we start to see the signature of the superconductivity. But the TC is onset is around 40K, but we can see that the superconductivity is still not very good not very high quality. So then our collaborators that help us to look at this stem of these samples, and we found out, okay, so our samples is the quality not so good. We can see that this 3 to 7 phase is a major phase, but we can also see this modular and trilinear intergrowth. And there are a lot of extended defects in the whole film. And but we see that if there are more fraction of 3 to 7 phase, it has a better superconductivity. So we start to trying to improve the sample qualities, and we recognize that in these bulk studies, there are several studies that already found out that there are some intergrowth of different RP phases, as also I mentioned in the previous talk. And Professor Jingguang Chen's group found out that if we have some precision doping into their bulk samples, it can remove this kind of in the growth. And also, Professor Joy Chen and Qigong Xue in South Tech has also independently they have found seen this when they have 5% of precision doping, the crystallinity of the thin film have been improved significantly. So we also tried this substitution with Presidium, and we found that indeed the crystallinity is much better. And also we found that in that interface, it is the 2 and 4 phase is often seen at the first layer. And the second challenge that we noticed is it has a very good narrow growth windows for this through 7 phase. And you can see in this phase diagram, only this red yellow region is a phase stability zoom of the through 7 phase. And we have systematically changed this growth condition. And the key of this image, this data here is that we found that with change of, for example, different oxygen growth pressure, we see there's a optimal pressure that have the best crystallinity and a stable C-axis lattice constant, and also with the best superconductivity. And the third challenge we found is that it's also already in the literature that this bilayer nucleus is very sensitive to oxygen deficiency. And what we have done is that we have built a homemade ozone annealing system that we can have a real-time feedback of resistivity during this oxygen ozone annealing process. So by doing this, we actually can map out a phase diagram of this ozone annealing. And the key here is that we want to optimizing competing factors. That is that we want to introduce more oxygen but without transformation into the other RP phases as shown in the red dots in this phase diagram. So after doing this, we finally realized a much better crystallinity, and we can observe the superconductivity transition temperature with onset above 48 Kelvin and with T0 above 30 Kelvin. And also we did this critical current density measurement. We have improved this critical current density 100-fold. But this number is actually still 10 times more than infinitely nucleates and 1,000 times more than cuprates. That means there are still a lot of room for the improvements. And also in the manifold, implant and out of manifold, we have found that this superconducting thickness matches with the thin film thickness, which means that it is a bulk superconductivity, and also implant coherent length around 1.7 nanometer, similar to bulk bilayer nucleates or cuprates. So next, I would like to go to our latest results on the supernuclear films on this LAO substrate. If we look at the lattice constant of this SLAO, LAO, and bilayer nucleates, we can see that the LAO is almost around half of the strength if we count it compared to this SLAO. So till now that the SLAO is only the substrate that can host superconductivity. And previously we have attempted the growth of bilayer nucleus on LAO, but all failed. But if we look at the implant lattice constant versus TC, we can see that the lattice constant of the LAO is kind of like on the verge of this the existing data point that may or may not have the superconductivity. So we are very interested in trying to figure out what's the nature of this putative superconducting non-superconducting boundary. So whether it is like the continuous transition or whether it may be a first order like structural transition. And also our collaborator, Lopa, that they did a very interesting work. I think they have already talked about it yesterday. That they have seen that both this SAO and AO they have the similar in-plane this nickel plane tilting patterns, but in the tensor region they have I mean alternating kind of tilting, which is different. So this is also I mean makes it more interesting whether this binucleates on AO can also host superconductivity. Actually, since we have the experience on this optimizing this growth on this SLAO substrate, we also tried the similar things on AO substrate, and we found indeed because of its less strain, so it has a much wider growth, wider range of growth conditions, and also the film can grow a little bit thicker and also of higher quality. In this image that we show this XRD of our best. AO samples on AO versus on SLO. Indeed, we see the quality is a little better. And actually, our collaborator from CS Group, Baya Wang, has already seen this signature of sensitivity when he was optimizing the 327 growth on the AIO. So with this inside information, actually, we quickly we can reproduce and also optimize this superconductivity, and we can realize onset of around 12K and also the T0 of around 3K. And also, we see a very good dynamic response, so that it proves that this is indeed a superconducting signal. So now we can say that the strain required for superconductivity in this bilayer nucleus thin film is, I mean, we almost half it from the 2% to the minus 1.2%. And this magneto transport also show that this superconducting thickness around the same thickness of the film thickness, and the critical current measurement show that this critical current density is around 10 times smaller than the samples on SLAO. So before yeah, and after this, I would like to have some discussion on the properties of these two films. And one thing that we noticed, which we found is very interesting, that the normal state transport of bilayer nucleus on AO and SLO is pretty different. So here we show the RT of this samples on AO versus SLO. And we fitted this the normal state relativity by a parallel resistive formula, which is that basically this relativity is composed of one power law and plus one term this mod A for Rigel saturation relativity limit, and we found that this formula can fit this the whole normal state pretty well. And what we found is that this after we fitted it, we found that the power of this samples grown on AO is very robustly different from the power uh, uh, we obtained from the SAO. And we can see that from this SAO that it's like this power is equal to 2, which means it's more like a Fermi liquid behavior. But for this AO, this power is around 5 over 3. And at the same time, if we see this mod if regular saturation returns by fitting in both systems, they got a similar number. And if we go to literature, we find that actually this kind of power is I mean, also observed in other systems. For example, this cuprates in the overdoped region, there is a kind of crossover from this power equal to 1.6 to power equal to 2. And also we found that in for this perovskite nucleus and pressure or strain or thickness tuning, that they also shown this kind of similar transition between this n equals to 2 to n equals to 5 over 3. So we asked our theory collaborators what does this mean, and they see that there's they told us that the three-dimensional ferromagnetic quantum critical point match this n equal to 5 over 3 power. But here we think that it's not likely that this has a ferromagnetic fluctuation. So we also wondering whether this spin fluctuation could lead to this result, but this remains an open question. And if we compare with our this compressive strain and temperature phase diagram with this pressure versus temperature phase diagram, and this is what we got by now. And we can see that at a low compressive strain, there's a low Tc, and in normal state is a T to the power of 5 over 3. And the in a little bit higher strain, we have a T square normal state behavior and a little bit higher Tc. And if we look at the bulk phase diagram, I think maybe we are around here that which that the just at the onset of the subjectivity as in this bulk study, but we are not quite sure whether this is an appropriate comparison. But anyway, we have these two data points now, and we are very curious whether, for example, at the end of the superconducting dome, and whether there can be a conductivity point, and what's the role, what's the signature and the role of the spin density wave as discussed in many bulk studies, but in thin films we haven't seen such signatures. And also, because of in the bulk we see this T-linear resistivity at this optimal doped region. And we are also curious whether if we can have more compressive strain, whether the normal state can be also like T-linear behavior and the superconductivity transition temperature can be also higher. And so if we look at this bulk versus compressed strain this comparison, and here we plot the inclination constant versus Tc, and all these black dots are from the bulk, and all these colored dots are from the thin films. We found that these are actually follows a pretty good trend that in the high I mean at the low strain or low pressure they have a larger impedance constant. There are no superconductivity, but when it is getting smaller than this around the 3.8 angstrom, the superconductivity actually it shows up, and this trades pretty well. And but on the other hand, because of the difference of the nature of this pressure versus compressive strain, we see almost opposite trend in this the Tc dependent on the C lattice constant. In the bulk, because when we add pressure, the C is getting smaller and the Tc is going up. But in the thin film, when we have a larger implant, a larger compressed strain, the C is also this elongated, so it's like this kind of trend. And our new AL data is around here. And also, the other one thing is also interesting that the maximum TC in this thin film versus in this bulk, and the pressure is around only it is only around half. So we think that by looking at these two phase diagram, because of I mean this trend is follows better than this. So we think the atomic or electronic structures that in response to this implant constant shrinkage are the key to the superconductivity. Also, we already showed this different seems different implant nickel oxygen bond tilting patterns. Looks that this is pretty robust for both AO and SLAO samples grown both SLAO and AO, and also on both of the samples that the outer plane nickel oxygen bond is also straightened. Yeah, so the reason that why the TC is only half in strength sample versus in high pressure, we think there are maybe two possibilities. Because one possibility that if we look at the previous slides, maybe we just need a little bit higher implant compressive strength, and it may help to boost TC. And the other possibility that because of the internuclear coupling is weakened when the C let's count is elongated. So this may be harmful to superconductivity. But now we cannot say I mean which is more likely. And finally, because of we can now have thin films grown on at AO, And we now we have more one more interesting thing to do. Basically, we can decouple the strain versus interface degree of freedom in this strain nucleates. So if the interfacial electronics structure is a key, for example, this strontium doping or any way that this termination dependent. So this thin film grown on ALO and then on SLAO should be very different from the thin film directly grown on SLAO. And but if the strain is the key, the thin film grown on ALO and on SLAO will be similar to this thin film directly grown on SLAO. And indeed, we found that the latter is the case that we see. And so this is my conclusion and outlook. So basically, we have optimized thin film growth of the bionucleates on compressive strain substrate, and we found that this compressive strain is the key to the subconductivity, and this PR substitution and oxygen stoichiometry plays a very critical role. And we also found that the normal state and subconductivity state has some difference in these two kind of substrates. Thank you for your attention. Yeah.
Thank you very much. All right. Any questions, comments? I think Mike Norman. Mike?
Yeah, thanks. Very nice talk. We did some work a couple of years ago on the lanthanum nickelate, the perovskite, which is also very near an antiferrometric quantum critical point. And again, these were MB films grown on LSAT. And it turns out that the critical exponent, the resistivity exponent, is temperature dependent, actually, and is due to interplay between antiferromagnetic fluctuations and disorder. So it could be potentially that the difference in these exponents might be a disorder effect.
I see. Okay. So that means that if we can, for example, grow better films, you expect this critical exponent may be different.
Yeah, possibly. Yeah.
In that case, Mike, was there anything close to linear resistivity, or it's also like
Yeah. So in these films, actually, what you find is at very low temperatures, you cross over to linear T
okay,
in these films.
I see. Okay, that's interesting. Let's see. Han Hui Chen, please.
Yeah. Okay. Hello, Professor. Great talk. So you mentioned in your talk, you speculate that if you have even stronger compressive strain, you may get a linear in-T resistivity. Is that correct? If I hear it correct.
Yeah, I mean, this is only we looking at the phase diagram here because we believe that in the bulk study, I mean, this region, they don't have pretty much data because it's very close to a phase transition, right? So
Yeah.
basically, these data are empty, and maybe we are just I mean, around this region. That's why
But
that what we see is maybe different from what the bulk people see.
But if you look at your phase diagram on the right panel, if you reduce the critical strain, the exponential component changes from 2 to 5/3. So by continuity, one would naively guess that if you further lower the critical compressive strain, you may further reduce that exponential component to 1. So why you believe that you should go to the other way?
So I think, yeah, I don't have a very strong experimental evidence or to support or to support this. But yeah, this is I think more like a hand weaving discussion. So yeah.
Okay. Yeah, thank you.
Any other questions, comments? Maybe I can ask a question. So just stare at the right panel, just the schematics. So in addition to the uh, strain as the parameter, for each type of strain, is there some kind of doping that you can either control or not control that varies the TC?
Yeah, I think Yue Fenye's group in Nanjing University, they have tried to dope strontium into the into this bilayer nucleating films, and they see a kind of like a half of the dome,
Mm-hmm.
a spinning dome, that with a more hole doping, the subjectivity disappeared. Yeah.
But I thought that like even just I thought there was some suggestion that maybe from you that if you do annealing and this sort of things, part
Oh
of the
yeah, yeah.
effect
So
is to change the
we
doping.
can, yeah, we can do some annealing, and yeah, and also I think this may be relevant to, maybe I can show this. Yeah, so we can, for example, do the vacuum annealing, and vacuum annealing will create oxygen vacancies in the, I mean, the apical site.
Mhm.
And this effect, I personally think this might be more relevant to the disorder effect other than doping effect,
I
because
see. Okay.
yeah, so well, we can see that here, and I think this data, this is relevant to the Professor Michael Norman's question, that we indeed we also try to use this to tune this oxygen content, and we think it's more likely change this disorder, but we see this kind of like power is pretty stable if the sample have a optimal oxygen content. Yeah.
Mhm. Okay. Is there any further
Can
question?
I ask a question?
Yeah, Darshan, please.
Yeah.
Okay, very nice talk. Just on this page, I want to mention for the thin
Mm.
film case, uh, resistance approaches zero with a different behavior compared to the 3D Barker case. Whereas for 2D case, could be related to the 2D KT phase transition. So, I mean, the resistance approach to zero actually slower than the Barker case. Is that, have you compared this, your resistance with the Barker case?
So yeah, I think now I think this thin film, because the film is really thin, so and it's has a very sensitive to the any kind of disorder. So I kind of believe that if the film quality is better, this transition should be sharper. If we considering, for example, the cuprates, that in those really thin film, they can still get a pretty sharp transitions. And for example, if we compare to Bisco, and this bionic should be still more three-dimensional than those something like Bisco, right? So yeah, I think now this transition width may be, still disorder limited. Yeah.
Okay, thank you.
Okay. I think there are no additional questions or comments. Let me just make a announcement that I made at the beginning of the session that the videos of the morning of the first session talks are available from the website. That there's a link, and hopefully these talks during this session will also be available before the start of the next session. So with that, let's thank Yijun and all the speakers of this session.